You are watching session number 4 of the chapter Chemical Bonding and Molecular Structure. In the previous session, I started with the concept of covalent bonds and I discussed about valence bond theory and VSEPR theory, and I solved some examples to predict the shape of given compound. Similarly, in this session, we will see some examples of how to predict the shape of given molecules as well as hybridization concept. 5 examples I discussed in the previous session. So now I am going to move with the 6th example, and I am going to consider example that is XeF4. XeF4. Using the concept of valence bond theory and VSEPR theory, we'll see what would be the structure of XeF4, how many bond pair of electrons we have, how many lone pair of electrons we have, what about the bond angle, such concepts we will see now. First main thing is you need to know the central atom and the number of valence electrons of that. And 2 different methods I told you. One is write the atomic number of central atom and write the electronic configuration. Based on that, you will going to get the valence electron. One more method is you should know the central atom in which group it belongs, and if you know the group number, and from that also one can guess what would be the valence electron present in that. Of course, xenon and electronic configuration you can write 4d10, 4s2 and 4p6 we get. One more way is xenon belongs to 18th group element, noble gases, we have 8 valence electrons. So in case of xenon, xenon is a central atom, we have 8 valence electrons. So 1, 2, 3, 4, 5, 6, 7 and 8 we have. So next fluoride ion we have, that 4 fluoride ion, and 1 valence electron of xenon is going to mutually shared with 1 electron of fluorine. So similarly 4 F we have, so I am going to consider like this. So 4 sigma bonds can be formed by mutual sharing of electrons between 1 electron of xenon and 1 electron of fluoride ion, and 4 electrons are left with, and they exist as lone pair. This is 1 lone pair and this is 1 lone pair. So this is how there will be mutual sharing of electrons, and of course we have presence of lone pair of electrons, and presence of bond pair and presence of lone pairs can help us to guess what would be the geometry of the molecule. So number of bond pairs we will see. So number of bond pairs will be 4. So here 1, 2, 3, 4, and number of lone pairs of electron, pair, always the electrons will be in the form of pair, lone pairs of electrons, and we have 2 here. So therefore total number of electron pairs, total number of electrons pairs will be a number of bond pairs plus number of lone pairs. Bond pairs will be 4, lone pairs will be 2, and totally 6 we are going to get here. And now you should know, if the bond pair is 4 and lone pair is 2, and the shape would be square planar. The shape of the molecule is square planar, and we'll see about the bond angle. So what would be the bond angle present in XeF4? And the bond angle present in XeF4 is 90 degree. And now we'll see how actually the XeF4 structure looks like. And remember, we have 4 bond pairs and 2 lone pairs. Means these 4 electrons are involved in a bonding with F, whereas these 4 electrons exist in 2 lone pairs of electrons. So since the structure is a square planar, and here let me draw, that is xenon is the central atom, and you should know about how actually the bond angle you are going to get. So that I am going to explain, and this is actually 3-dimensional structure. You need to imagine how I am going to draw the structure of xenon. So here we have 4 covalent bonds which are formed with F. So I am going to consider here. So 4 we have. So these are the shared pair of electrons. So 2 lone pair of electrons will be present, and one will be present above the plane like this, and one will be present below plane B like this. So try to understand, this is a plane, this is what I have shown with the dotted. So imagine this is a plane, okay, and here if you consider as a plane, so 1 xenon, 1f, 2f, 3f, 4f, 4f will be present, and exactly at the center we have xenon, and one lone pair of electrons will be present above the plane. So above the plane one bond and lone pair of electrons, and below we have one, and we have one lone pair of electrons. So this is how this is a plane, and one will be above the plane and one will be below the plane, and this kind of shape we call it as a square planar structure. Actually, in the previous session, I gave hint how to get the shape of XeF4, but actually you should explain in this manner so that number of bond pairs, lone pairs is going to affect the shape of the molecules, and if only 4 bond pairs are present, without any lone pairs, we would have said that the structure will be tetrahedral, but we have 2 lone pairs of electrons. Therefore, the presence of lone pairs of electron disturb the geometry of the molecule. And now you try to remember the angle here, it is 90 degree, and if you just see that one, and you need to imagine how this molecule looks like. As I said, so this will be the plane, and we have one lone pair of electrons above. Therefore, the bond angle will be 90 degree. You just try to know that one. Okay, so this is the bond angle. The same if you consider this bond angle also, this bond angle also, the bond angle is 90. This is how the shape of XeF4 can be predicted. And we'll see the next one, 7th one. And now 7th one I am going to consider PCl5 as an example. PCl5. And valence electrons first we need to know. So phosphorus atomic number is 15, and you can write the electronic configuration based on that. We would have said that the number of valence electron will be 5. One more method is phosphorus belongs to group number 15, nitrogen, phosphorus, isn't it? So phosphorus belongs to group number 15, so I can say 5 valence electrons we have. So 1, 2, 3, 4, 5 valence electrons of phosphorus we have, and 5 chloride ions we have. So mutual sharing of electrons of 1 from the phosphorus to 1 from the chlorine. So 5 Cl minus is going to mutually shared, and we will see the number of bond pairs. So number of bond pairs, shared pair of electrons, that will be 5, and we will see number of lone pair of electrons. Lone pair of electrons 0. We don't have any electrons left without bond formation. Therefore, now we will see number of electron pairs. Number of electron pairs in this case, that is the sum of bond pairs plus lone pairs. Bond pairs will be 5 and lone pairs will be 0. Therefore, the number of electrons pairs will be 5. And we will see what about the shape. Okay, so try to imagine if we have 5 bond pairs of electrons and without any lone pairs of electron, and what would be the shape of the molecule? The shape of the molecule is trigonal, bipyramidal. Trigonal, bipyramidal will be the shape. And what about the bond angle? Bond angle in this case, so we have 2 bond angles, one is 120 degree and one more is 90 degree. So we'll see now how actually trigonal bipyramidal looks like, and how we can mention the bond angle 120 and 90. See, I am going to draw the shape of PCl5, phosphorus pentachloride, you can consider. So trigonal bipyramidal. So P, phosphorus we have in the center, and let me draw the trigonal structure like this, and you need to imagine how I am going to show here. So this is a trigonal shape what I can consider, and we have 3 bonds in a trigonal fashion, and Cl I consider. So 3 Cl bonds, 3 PCl bonds will be in this shape. And this is a plane you can consider, and one more Cl bond will be here, that is above the plane, and one more will be here, that is below the plane, you can consider. And as we know, in case of a trigonal planar, the bond angle will be 120 degree. See here, this one bond angle is 120 degree. If you consider PCl bond and PCl bond, this bond angle is 120. Similarly, this bond angle is 120. Whereas one PCl bond is above and one more PCl bond is below. So in that case, if you consider the bond angle of these two, this would be what actually 90 degree. This is how actually PCl5 looks. We have trigonal bipyramidal shape and 2 different bond angles we have, and you need to imagine the plane we have, and one PCl is above and one PCl is below. This is how PCl5 looks like. One more example we will see. I am going to talk about SF6. SF6 sulfur, right? Atomic number 16 we have, and we can guess the number of valence electrons, and sulfur belongs to group number 16, isn't it? So oxygen family sulfur belongs, therefore 6 valence electrons we have, 3, 4, 5 and 6 valence electrons we have, and we have 6 fluoride ions and a mutual sharing of 1 electron of sulfur with the 1 electron of fluoride ion, therefore 6 bond pairs are going to observe, and there is no presence of lone pair of electrons. I can say number of bond pairs will be 6 and number of lone pairs will be 0, and the total number of electron pairs in this case of SF6 is the summation of BP plus LP, that is 6 plus 0, we are going to get 6. So now we will see what about the shape of a molecule if bond pairs are 6 and no presence of a lone pair of electrons. I hope you can guess, the shape will be octahedral. The shape will be octahedral, and bond angle we will see now. And bond angle in this case of octahedral is 90 degree. We will see how this SF6 looks like. So sulfur we have in the middle. So along with that we have 6CF. So just try to know how actually octahedral structure looks like. So let me draw the plane so that it will be easy for me to show actually how 90 degree we are going to get. Otherwise you won't able to recognize how actually bond angle will be 90 degrees. So SF, so 4F will be in this position, and this is the plane, and 1F will be above the plane and 1 will be below the plane. So SF6, and this shape we call it as octahedral in shape. So this plane what I mentioned, that is the plane, and one SF will be above the plane and 1 will be below the plane, and now you can guess the bond angle between these two is 90 degree. You can consider any bond angle, because of course these two are 90 degree, okay, and one is above the plane and one is below the plane, therefore 90 degree you are supposed to mention here. So that is how the shape of SF6, that is octahedral in shape, and 90 degrees we have. So now you need to think over using VSEPR theory, and by knowing the bond pairs of electrons and lone pairs of electrons, we can identify the shape of given molecule. We will see what would be the shape of IF7. Iodine, which belongs to group number 17, from that I can say we have 7 valence electrons, 3, 4, 5, 6, 7, and we have 7 fluoride ions, mutual sharing of electrons between one of F and one of I, and I have the 7 bond pair of electrons like this. So no electrons left. From this I can say number of bond pairs will be 7 and number of lone pairs will be 0. Number of electron pairs in IF7 is equals to sum of bond pairs plus lone pairs of electron, and the answer will be 7. If we have 7 bond pairs of electrons and the shape of the molecule is pentagonal bipyramidal. Pentagonal bipyramidal will be the shape, and in pentagonal bipyramidal we have 2 different kinds of bond angle. One is 72 degree and one more is 90 degree. We will see now how actually IF7 looks like, and how we can mention the bond angles as 72 and one more is 90. And here I am drawing the pentagonal shape, and later we will draw 2, one will be above and one will be below as like pyramid. So here one IF bond we have, bond pairs of electrons these are, and in pentagonal structure where it is going to mention that is 5 IF bonds we have, and we have 2 more IF bonds, and one will be above the plane like this and one will be below the plane like this, and here as I mentioned, the below the plane, this bond is going to be linked with I and F. Since it is below, I am going to mention like this. And the bond angle between IF and IF in the pentagonal structure, that is 72 degree. And one will be above IF, and here the IF of the bond angle which is present in pentagonal, and this bond angle is actually 90 degree. This is how the structure of IF7 can be predicted using VSEPR theory. Using VSEPR theory, not only we can predict the shape of the molecules, but also we can predict shape of ions. So the next example what I considered is BF4 minus we have, that is ion, and I will see how the shape of ions can also be predicted. So BF4 minus, central atom is boron, which belongs to group number 13, and 3 valence electron I am supposed to mention. And we have 4, the fluoride ions. We have 3 valence electrons from boron, but we have a minus over here. We know that when an ion is formed by the gain of electrons, 1 electron will be extra. Therefore, 1 extra electron I am going to mention here, and this is because of minus of what we have. And therefore, 1 electron of boron is going to be mutually shared with 1 electron of F, and similarly 4 F we have, and 3 F of the 3 electrons of boron, and 1 more electron we have. Since it is minus, therefore I can mention the 4 F's like this. So now bond pairs in case of BF4 will be 4, and lone pairs it is 0. Then number of electron pairs we can predict as bond pair plus lone pair. 4 number of bond pairs we have, therefore total number of electron pairs will be 4. Now we will see what is the shape of this molecule. As we know, if we have only 4 bond pairs of electrons without any lone pairs, and I hope you can guess, the shape would be tetrahedral. Tetrahedral is the shape. And bond angle in tetrahedral molecule, as we know, 109.5 degree we are going to get. So now we'll see how actually BF4 minus looks like. So now just to see, we have a B over here, and all the F's will be going to occupy the corners of the regular tetrahedron. So this is how the tetrahedral shape can be represented, and 1 minus we have, that is going to be mutually shared with the F. Therefore 1 F I am going to represent it as minus, and the bond angle you can mention, that is 109.5 degree. That is how for ions also we can predict the shape, and you need to remember minus we have, therefore 1 electron extra you need to be considered. One more example of the same kind we will see, that is PF6 minus. This is also ion. Phosphorus belongs to group number 15, and from that I can say 5 valence electrons we have. So 1, 2, 3, 4, 5 valence electrons we have, and 1 minus we have, that is 1 electron extra we are supposed to mention, and 6 F's I have here. So I can represent a mutual sharing of electrons of each electrons of phosphorus with 1 electron of fluorine. Remember, the last electron is contribution from that minus in the formula what we have. And here the number of bond pairs will be 6 and lone pairs will be 0. And the number of electron pairs one can guess, that is bond pair plus lone pair. The number of bond pairs we have 6, there is absence of lone pair of electrons, therefore number of electrons pairs will be 6. And now you guess what would be the shape. If we have 6 bond pairs of electron, the shape is octahedral in shape, and if the molecule shape is octahedral, and guess what would be the bond angle in this case. The bond angle is 90 degree. And I hope you remember how actually octahedral molecule looks like. Phosphorus in the middle. We have seen such kind of shape already. So this is a plane what I can consider, and out of 6 the 4 PF bonds will be like this, and 1 PF bond is above the plane and 1 will be below the plane, and one electron is going to be shared with 1f. For 1f I am going to mention minus here, and if you calculate the angle will be what, actually 90 degree here. So these two are the types of ions. For ions we predicted the shape of the molecule. And one more example I am going to consider, that is example number 12, and what I am going to consider here is SnCl6 2 minus, SnCl6 2 minus, and this I am going to solve here. I will give you hint, but you need to try on your own, and you can predict the shape and the bond angle present in that. The hint what I am going to give here is Sn tin belongs to carbon family, group number 14. We have 4 electrons, 4 valence electrons, right? The charge is 2 minus. So how many ions we have extra? We have 2 electrons extra. 2 electrons we have extra. And how many chloride ions we have? 6 we have. So here this is for the 1, 2, 3, 4 and 5 and 6 we have. And now you remember how many bond pairs we have? 6 we have. How many lone pair of electrons we have? 0. And now you guess what would be the shape and what would be the bond angle, and how you can show the shape of SnCl6 2 minus, and that you have to try. And all these are the examples I can solve to predict the shape of molecules as well as ions based on VSEPR theory. We will learn the concept of hybridization. We know that we have different atomic orbitals with different shape and different energy. S orbital, P atomic orbital, D atomic orbital we have, spherical in shape, dumbbell in shape, double dumbbell in shape, we know that one, and energy of these atomic orbitals will be different. Whenever the mixing of atomic orbital takes place, as I said, these atomic orbitals which are going to mix, they have different energy and different shape. When there is intermixing of such atomic orbitals, there will be formation of new atomic orbital which is going to have the same energy or equal energy, I can say, and these new orbitals we call it as hybrid orbitals, and the process we call it as hybridization. Intermixing of atomic orbitals of slightly different energy to get same energy atomic orbitals, particularly we call it as hybrid orbitals, and the process is called hybridization, and the new orbitals that are going to be formed is termed as hybrid orbitals. Remember that before hybridization atomic orbitals will be of different energy. After hybridization, if we get the hybrid orbitals, the energy will be same, and that is termed as hybridization. The statement, as I mentioned, intermixing of atomic orbitals of slightly different energy to get hybrid orbitals of same energy is called hybridization, and the new orbitals formed are called hybrid orbitals. Now we will see what would be the salient features of these hybridizations, and you need to remember, because these points are going to help us later to solve some examples. The first one is quite important one. See that one, the number of hybrid orbitals produced. After intermixing of atomic orbitals, we get hybrid orbitals. As I said, the number of hybrid orbitals produced is equals to number of orbitals undergoing hybridization. Let us assume I have 2 orbitals, 2 atomic orbitals, and they are going to intermix and we are going to get hybrid orbitals. So 2 atomic orbitals are going to intermix, means the hybrid orbitals you are going to get, that is also 2. The number of orbitals which are going to intermix, that will be as same as the number of hybrid orbitals or new orbitals what we are going to consider. So if you consider one s atomic orbital and one p atomic orbital, and a hybrid orbital will be sp, and 2 sp atomic orbitals we are going to get here. This is the example what I can say. The hybrid orbitals are always equivalent in energy and shape. As I said, after getting the hybrid orbitals, there is no variation in the energy as well as shape. Identical or equivalent energy and shape we can guess here. The hybrid orbitals can form strong bonds here. If you compare the atomic orbitals as well as hybrid orbitals, and the stronger one is the hybrid orbitals because they are more directional in nature and hence overlap to greater extent. We know that one, the atomic orbital will be directional in nature, whereas hybrid orbitals are directional, or I can say more directional in nature, because the presence of a shared pair of electrons will be exactly in the center of combining the nuclei, I can say, and because of that the hybrid orbitals will be stronger and they are more directional, and overlapping is also more when you compare with the overlapping of atomic orbitals. As I said, the hybrid orbitals are directional in space, and why they are directional in space? To minimize the repulsion between the electron pairs. As we know, according to valence shell electron pair repulsion theory, the electrons, the charge will be negative, and if you have two adjacent electrons, they repel each other. So therefore what happens, they will be in a particular direction in a space to avoid repulsion. So if they avoid repulsion, and what I am going to say, that structure will be quite stable. And remember, if they are directional in stature and they are going to minimize the repulsive force, so that is the quite stable. And what is the main application of this hybridization is, we can predict the geometry and bond angle by knowing the hybridization also. That is the main point or the main application of the concept of hybridization. So we came to know that intermixing of atomic orbitals of slight different energy to get hybrid orbitals of same energy, we call it as hybridization, and we discuss some main points regarding hybridization. Examples we'll see to know the concept of hybridization. The first example I am going to consider here is the formation of beryllium chloride, BeCl2. We'll see what would be the hybridization. Based on that, what would be the geometry and the bond angle present in BeCl2. Atomic number of beryllium is 4. The electronic configuration of beryllium is 1s2 and 2s2. Number of valence electron in beryllium is 2. 2s will be the outermost shell, and therefore the number of electrons, valence electron, will be 2. To explain the concept of hybridization, as I mentioned, there will be intermixing of atomic orbitals. Therefore, the representation of atomic orbitals helps us to predict the hybridization. So what I am going to consider now, I consider beryllium in ground state. Beryllium in ground state. How we can represent the atomic orbitals? We know that one, for S we need one atomic orbital. This is for 1s, and for 2s this is for 2s, and since in the excited state I need 2p electrons, therefore I am going to draw it here for the p, and we know that one we have 3 atomic orbitals for p, px, py and pz, and this is for the 2p. So this is how the electron distribution we are supposed to consider. In 1s atomic orbital we have 2 electrons. According to Pauli's exclusion principle, electrons of opposite spin can only be paired. In a 2s atomic orbital we have 2 electrons. We need to represent like this. This is the beryllium atom in a ground state. Now we'll see what about in excited state. Excited state of beryllium, and how we can represent that. When beryllium gains certain kind of energy, there will be a shift of electrons from one atomic orbital to another atomic orbital, and that is how we can represent that as excited state. So this is the atomic orbital of 2s, and here I am going to represent for the 2p. Okay, and now we will see how actually there will be excitation takes place. 2s atomic orbital we have 2 electrons, and one electron from 2s is going to jump into atomic orbitals of 2p. So in the 2s we have one electron, and in 2p we have one more electron. So there will be shift of electrons from 2s to 2p, and one electron is going to shift. And now in the excited state we have one pair of electron. This is unpaired electron, this is also unpaired electron. So now we'll see what about in hybridized state, beryllium in hybrid state. What happens when there is a hybridization, hybrid state we call it as, and let me draw the shapes. This is for 1s, and we have 2 electrons, and this is for 2s, we have only one electron over here, and this is for the 2p, we have one electron in one of the atomic orbitals of 2p, and here I am going to represent that. So this is in the hybrid state. We'll see how does actually hybridization takes place. As I mentioned, in hybridization there is intermixing of atomic orbitals of different energy. So we have 2 atomic orbitals, one is 2s and one is 2p. Of course the shape is different and energy is also slightly different. And what happens, there will be intermixing of these two, so that hybrid orbital of equivalent energy is going to be produced. So what I am going to say here is, we have one, observe here, we have one 2s atomic orbital and we have one 2p atomic orbital. So that there is an intermixing of these two, they are going to mix each other, and that produces one hybrid orbital, and that we call it as sp. So 2 sp hybrid orbitals we are going to get, 2 sp hybrid orbitals. So this is s and this is p. So sp hybrid orbitals we are going to get, but remember, number of sp hybrid orbital will be 2. As I mentioned in postulate 1 of hybridization, the number of atomic orbitals they are going to mix will be same as the number of hybrid orbitals what we get. So 2 atomic orbitals are going to intermix, means 2 hybrid orbitals we are going to get. Since we have s and p, therefore sp hybrid orbitals we get, and how many? 2 sp hybrid orbitals we are going to get. So these two are hybrid orbitals of the same energy, and that hybrid orbital name is sp hybrid orbitals. And 2 we have. Later what happens, these 2 sp hybrid orbitals, they are going to overlap with the orbitals of 2 Cl atoms. So now if you consider the BeCl2, we have a 2 Cl, isn't it? So they are going to overlap, these hybrid orbitals, they are going to overlap with the orbitals of 2 Cl atoms. And how does the overlapping takes place? And this is one hybrid orbital, this is one hybrid orbital. In a Cl we have one valence electron we know, and one Cl is going to overlap, or the shared pair of electrons here, and this one electron will be from what, actually one more Cl, and this is how there will be hybridization takes place. So now this is how I can show the region of hybridization. And what kind of hybridization is this? This is sp hybridization. This is sp hybridization. So these 2 electrons are of beryllium, and these 2 electrons are of 2 Cl atoms. This is how we can represent, and the same I have written here, 2 sp hybrid orbitals, they are going to overlap with the orbitals of 2 Cl atoms. And when there is overlapping of 2 Cl atoms, there will be formation of 2 BeCl bonds. So 2 shared pair of electrons we have, means there will be formation of 2 BeCl bonds. This is how the hybridization takes place, and the name of hybridization is sp hybridization. So 2 sp hybrid orbitals, they are going to overlap with orbitals of 2 Cl atoms, and we get 2 BeCl bonds. So how we can represent that? So if you consider beryllium, as we know, this is 1 sp hybrid orbital, this is 1 sp hybrid orbital of beryllium, since we have 2 sp hybrid orbitals. and we have two Cl atoms. This is one Cl I can consider, and this is one Cl I can consider. So the atomic orbital of this Cl is going to overlap here, and atomic orbital of this Cl is going to overlap here, and here there is what actually intermixing, or I can say the hybridization takes place, and there is head-on overlapping of atomic orbitals, and the bond will be sigma. You can represent this is the sigma bond formation, and this is the sigma bond formation what we can get. And the same structure I can represent in very simple manner Be, and this is how there will be hybrid orbitals to form a bond. Therefore BeCl we have, and here also BeCl we have, and the bond angle is 180 degree, of course we can get, and one can guess the shape of this molecule, and the shape of this molecule is linear in shape. So this is how the hybridization can be predicted, and the shape and bond angle depends on the type of hybridization. Remember, here we got sp hybridization, and we got a linear shape with the bond angle 180 degree, and that is all about the first example what I can consider, beryllium chloride. Second example, BF3. Number 2, BF3. We'll see the hybridization involved in BF3. Atomic number of boron is 5. Electronic configuration is 1s2, 2s2, 2p1. Number of valence electron will be 3. This is the first shell, and these two are the second shell. Number of valence electrons will be 3. We'll see now the boron in the ground state, how we can represent the structures. And boron in ground state, the first one will be 1s2. This is for 1s atomic orbital, and we have 2s2, so this is for 2s, and we need one more of p, which is px, py, pz, and 3 atomic orbitals I am going to consider. This is for 2p. So now we'll fill the electrons. So in 1s we have 2 electrons of opposite spin I can represent. 2s2 we have 2 electrons, and in a 2p1 we have 1 electron I am going to fill here. Now I consider the boron in excited state. In boron in excited state, we'll see. Boron in excited state, this will be the electron which is present in 1s. And what happens in case of excited state, as I mentioned, there will be shifting of electrons from one atomic orbital to another atomic orbital. So we have 1 electron over in a 2s. So 1 electron from 2s atomic orbital to shift to 2p atomic orbital. So we have 1 electron over here, and here we have 1 electron already of boron, and 1 more electron. There is a shift of electrons from here to here, you can say, and that is how the boron in excited state. Now we'll see boron in hybrid state. Boron in a hybrid state, what we can represent. So we'll see that what kind of hybridization takes place, and let me draw the initial structures, and later we'll see how actually hybridization of these takes place. In a 2s atomic orbital we have 1, and in a 2p we have the electrons, 2 electrons after excitation we have. So this is how we can mention the boron in the ground state and the boron in excited state. Excited state it is, boron in excited state, and hybrid state, this is how we can represent. So now if you observe the atomic orbitals what I can mention, and this is one, the valence shell, 2s2 and 2p1, therefore you need to consider this atomic orbital and this atomic orbital also, and here we have 1 2s atomic orbital and 2 2p atomic orbitals. Let me write that. So we have 1 2s atomic orbital, and we have 2p, that too 2, so therefore we have 2 2p atomic orbitals. These are the atomic orbitals of different energy and different shape, they are going to intermix, and the hybrid orbital what we are going to get, that will be of the same number. So how many atomic orbitals we have 1 and 2 we have, and totally the number will be same, therefore we are going to get 3, isn't it? So 3 hybrid orbitals we are going to get. So 3 hybrid orbitals. So what kind of hybrid orbitals? This is S and this is P and this is P. Therefore 2 S3 sp2 hybrid orbitals. Hybrid orbitals we are going to get here. So 1 S and 2 P we have, therefore sp2 hybrid orbitals. Since we have 1 S and 2 P, and we are going to get 3 sp2 hybrid orbitals. So these 3 sp2 hybrid orbitals, they are going to overlap with, so these hybrid orbitals, they are going to overlap with orbitals of 3 F atoms, isn't it? So that I am going to write here, they are going to overlap with the orbitals of 3 fluorine atoms. So how does the orbital overlapping takes place? And let me explain this in the structure of hybrid orbitals. So we have this is 1 sp2 hybrid orbital, this is 1 sp2 and this is 1 sp2, 3 we have. And F has 1 valence electron, so 1 electron from F will be here, and remember that electron will be of opposite spin. So this electron is from F and this will be 1 more F and this will be 1 more F, 3 Fs we have. And this is how the main part of hybridization this is. And now I hope you can guess what kind of hybridization takes place. 1 S and 2 P, therefore hybridization will be sp2 hybridization, what we are going to get, sp2 hybridization. So when 3 sp2 hybrid orbitals overlaps with orbitals of 3 F atoms, and there will be formation of what actually 3 BF bonds. So in BF3 we have 3 BF bonds. So how actually these 3 BF bonds looks like? So boron in the central, and as we know we have 3 sp2 atomic orbital. This is how we can represent. This is the one and this is the second one and this is the third one. Of course we can represent the smaller nodes which actually represents the sp2 hybrid orbitals, and 3F we have. So this is the 1F, and hybrid or the atomic orbitals of F is going to overlap over here, and if I consider F over here, and this is how there will be overlapping, and if I consider F over here, and this is how there will be overlapping of hybrid orbitals of boron and the atomic orbital of F. And this is, since head-on overlapping, sigma bond is formed and sigma bond is formed, and here also sigma bond is formed. In simple, I can mention the shape as like this. There is a bond between B and F like this, and this is how I can mention one more BF bond and one more BF bond. So 3 BF bonds we have. And now you can guess what would be the shape. The shape will be trigonal planar. The shape of BF3 will be trigonal planar, and the bond angle is 120 degree. So this is how we can represent the geometry and what will be the bond angle, and the type of hybridization involved in BF3 is sp2 hybridization. Example number 3, methane. CH4. Atomic number of carbon is 6. Electronic configuration of carbon 1s2, 2s2, 2p2. Valence electron will be 4. Now we will see the carbon in the ground state. How we can represent that? And this is for 1s, and this is for 2s, and for 2p we need 3 atomic orbitals, px, py and pz. This is for 2p. Now we will distribute the electrons. 2s we have a pair of electrons. In here also we have 2 electrons, and in 2p atomic orbitals we have 2 electrons. According to Hund's rule, you have to fill first all the atomic orbitals has to be filled with one electron. Later, if you have electrons, the pairing of electrons starts. Now we'll see carbon in excited state. Carbon in excited state, so we have 1s here, and this is the atomic orbital of 2s, and for 2p this will be the atomic orbital what I can consider. In excited state, the electron will shift from 2s to 2p, so one electron is going to be shift over here, so therefore one electron we have here, and the shifted electron you are going to get in this atomic orbital, pz atomic orbital you can say. So now carbon in hybrid state, we'll see carbon in hybrid state. So how actually hybridization takes place, and before moving with the atomic orbitals, we'll just write as it is in case of excited state what we are left with, and later we'll see the one more atom we are going to consider is hydrogen, and how does intermixing and later overlapping takes place. We have one electron each in the atomic orbital of 2p you can say. So this is in the hybrid state. So now if you observe what are the atomic orbitals are going to involve in the hybridization. So 2s to 2p, 2p2 will be the valence shell. This is the reason why I underlined there. So 2s, we have a 1 2s atomic orbital. So let me write here 1 2s atomic orbital we have, and we have a 2p atomic orbital. How many we have? 3 we have. So here I am going to consider we have 3 2p atomic orbital. They are going to intermix. So there will be intermixing of 1 2s and 3 2p atomic orbitals, and the number of hybrid orbitals will be same. So therefore 1 and 3 we have, therefore we are going to get to 4 hybrid orbitals. What would be the name of hybrid orbitals? S and 3p we have, therefore the name will be sp3. So 4 sp3 hybrid orbitals we are going to get. And one more element is hydrogen. So these 4 sp3 hybrid orbitals, they are going to overlap with orbitals of, they are going to overlap with orbitals of, how many hydrogen we have? 4 hydrogens we have. They are going to overlap with orbitals of 4 hydrogen atoms. So how does the overlapping takes place and what kind of hybridization we will see now. So we have 1 2 3 4 sp3 hybrid orbitals. We have 1 electron each over there, and if you consider 4 different hydrogen, one electron is going to be mutually shared, and this is 1 electron of 1 hydrogen, and this is 1 electron of one more, this is the third one, and this is the fourth one. So now this is actually all these are responsible for the hybridization, and now you can guess what kind of hybridization took place. 1 2 3 4 S and 3p, therefore the hybridization is sp3 hybridization. sp3 hybridization is going to take place in case of methane. So now what is going to be formed at the last? So therefore we are going to get what actually 4 carbon hydrogen bonds we are going to get in the final because of the hybridization. We will see what would be the structure of that one. This is the carbon we have, and for carbon we have 4 sp3 hybrid orbitals. So this is the first one I can consider, this is the second one, and this is the third one. You can consider this is the fourth one, and we have 4 hydrogens. Hydrogen we have only 1 electron, therefore the atomic orbital shape will be spherical. Therefore this is how for this 1 hydrogen there will be overlapping of atomic orbitals. This is how for the 1 more hydrogen, and this is for the third hydrogen, and this is for the fourth hydrogen. There is a head-down overlapping of hybrid orbitals of carbon and atomic orbitals of hydrogen. Sigma bond is formed everywhere. So therefore total number of sigma bonds will be 4. And in simple we can represent like this. This is the shape of methane, and all the hydrogens will occupy the corners of the tetrahedron, and I hope you remember the angle between these, that is 109.5 degree is the bond angle, and the shape will be tetrahedral. Now we came to know that the methane possesses the hybridization that is sp3. Fourth one, ammonia I consider. We will see the hybridization involved in ammonia. Atomic number of nitrogen is 7. Electronic configuration is 1s2, 2s2, 2p3, and the number of valence electron in nitrogen is 5. Now we'll see the nitrogen in ground state. We'll represent in the same fashion. This is 1s. This atomic orbital is for 2s, and one more atomic orbital we have, that for p. This is for 2p. Now we will fill the electrons. In 1s we have 2 electrons in the form of pair. In a 2s we have 2 electrons. In a 2p we have 3 electrons. Fill according to Hund's rule. Therefore 1, 2 and 3 I am going to consider. So now we will see the nitrogen in hybrid state. Nitrogen in hybrid state. There is no question of excited state. Why? Because all the p atomic orbitals are singly occupied. There is no question of excited state here. So in hybrid state, what happens and what kind of hybridization takes place, we'll see now. Let me draw the atomic orbitals as same as what we have in case of ground state. Now you try to know the number of valence electrons present in a nitrogen is 5. In all the cases, you need to consider the 2s and 2p atomic orbital. This is one 2s atomic orbital and this is the 2p atomic orbitals. So now we'll see how actually the hybridization takes place. So how many atomic orbitals are involved? Remember that in a chemical bond formation, there will be involvement of a valence electron, that is nothing but the atomic orbitals of valence electrons. So 2s is involved as well as 2p is involved, underlines that one. So therefore this also is going to involve and these also are going to involve. So we have one 2s atomic orbital. So I am going to write here, we have one 2s. And how many 2p we have? We have 3. So we have 3 2p atomic orbitals. They are going to intermix. So there will be intermixing of 1 2s and 3 2p, and I hope you can guess how many hybrid we get. 4. 1 plus 3, 4. And what type of hybridization? Yes, and we have a 3p. Therefore 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. Then out of 4 sp3, don't think that all the 4 are going to involved in overlapping of atomic orbitals of hydrogen, because observe here, this is 1 and these are the 3. So out of 4, 1 has already the electron pair. So since there is one hybrid orbital is going to contain the lone pair of electrons. So out of 4, 1 has the lone pair of electrons, means they are not going to involved in bonding. So it has one pair of electrons, they are not going to involved in bonding with the hydrogen. These 3 are the electrons which are going to involved in hydrogen. Therefore this will be the lone pair and these are the bond pairs. So out of 4 sp3 hybrid orbitals, 1 hybrid orbitals contains a lone pair of electrons. Therefore we are left with 3, isn't it? We are left with 3 sp3 hybrid orbitals. So out of 4, 3 we are left with, and these 3 hybrid orbitals, they are going to overlap with atomic orbitals. They are going to overlap with orbitals of what we have. We have 3 hydrogen atoms. They are going to overlap with 3 hydrogen atoms. When there is overlapping of 3 hydrogen atoms, how the overlapping takes place? So this is the lone pair of electrons. We are left with 3 hybrid orbitals. Already it has 1 electron each, and this electron is from one hydrogen, this is from another hydrogen, this is from third hydrogen. Therefore, the type of hybridization what we are going to get here is, this is 1 and we have a 3p, therefore hybridization will be sp3 hybridization. The kind of hybridization what we get is sp3 hybridization. So because of sp3 hybridization, and we are going to get what actually three NH bonds. 3 NH bonds we are going to get. And now we'll see the shape of that. So nitrogen we have, and as I mentioned, 4 sp3 hybrid orbitals, and out of 4, one has lone pair of electrons. So let us assume this is a hybrid orbital, we have one lone pair of electrons. This is the representation of these two electrons, one electron, one electron, one electron, one electron, in the form of pair, and they are not involved in bonding, therefore that we call it as lone pair of electrons. We have, this is the one hybrid orbital, this is one sp3 hybrid orbital, this is one sp3 hybrid orbital, the main orbital I mentioned, and of course we have one more kind of lobes. I mentioned only the main, and we have 3 hydrogen atoms. There will be this is spherical shape, one electron we have for the hydrogen, and this is the one, and this is for the one more hydrogen, and this is for the one more hydrogen what we have. And here sigma bond is formed since the head-on overlapping of hybrid orbitals with atomic orbitals takes place. And in simple, I can mention the nitrogen we have, and one lone pair of electrons we have on the nitrogen, and 3 hydrogens will be present in the 3 corners of the tetrahedron, and the bond angle between these is 107 degree. And now you can predict the shape will be pyramidal. That is how the hybridization of ammonia is sp3 and the shape is pyramidal, the bond angle is 107, but remember ammonia has one lone pair of electrons.